Hi, everybody. As promised, we're continuing. This is 6.2, and we did kernel. We said we're going to do kernel and range. Well, the kernel is a subset of the domain V. The range is a subset of the codomain W. So that's important. So that they're in two different places. The kernel is in the domain V. The range is in the codomain W. So they live, the kernel and the range live in different places. Okay, well, just like the kernel turned out to be a subspace of V, the range turns out to be a subspace of W. Meaning, if you look right here, the range of T is a linear transformation, is a subspace of W. The range of a linear transformation T from V to W, two vector spaces, is a subspace of W. And that's actually pretty easy to prove. First of all, we know that the range is non-empty because we know that T of 0 is equal to 0. So we know at the very least the range contains a zero vector. Now we just have to show that it is closed under addition and scalar multiplication. That is not hard at all, and that's going to come, as I say, from the linearity. So if T of U and T of V are vectors in the range, see, U and V are part of the domain capital V, but T of U and T of V are members of the range of which is a subset of the codomain W. Anyway, U and V are in the are part of a vector space, which means U plus V is also part of that same vector space V. So so we know by definition of linear transformation that the sum of T of U plus T of V is equal to T of U plus V. But since U plus V is a vector, so T of U plus V is in the range, which means T of U plus T of V is in the range. So we've now shown that if we take two elements that are in the range and add them up, we get a third element which is also in that range. And to show closure, pretty much the same idea. T of U is going to be a vector, and C is going to be a scalar. And now, since U is part of V, so CU is also part of V. So therefore, and we know that C of TU is equal to T of C times T of U is equal to T of CU. But again, T of CU, that's just a T of a vector, so that it also is by definition in the range. So the range is closed. That makes it a vector space. So the kernel and the range of a linear transformation are subspaces. Now, to find now we in the previous section in the previous video, this section, but the previous video, we found the kernel. The basis for the kernel of linear transformation, and now we're going to find the basis of the range of the linear transformation, which is defined by a linear transformation, which is defined by a matrix multiplication. So the range is all vectors B such that the system AX equals B is consistent. And so basically all the possible B's I can get out here, that's going to be my range. So let's take a look here. Now remember, the A's here are fixed. A is a fixed matrix. So all these A's, A1, A2, A22, A2, whatever, they're all fixed numbers. But the XY, the X1, X2, Xn, these are variables. Just realize that. But when I do a matrix multiplication, we learned that I could rewrite it this way: X1 times the second column, X3 times the third column, Xn times the nth column, just like that. And all that combined is going to be equal to this B column. So again, AX equals B. Now, by definition, B is in the range of T if and only if B is a linear combination of the column vectors. So therefore, the column space of matrix A is the same as the range of T. Isn't that awesome? The column space of the matrix A is the same as the range of T, because that's because this guy here, this is what the column space is. So that is just awesome. And we have here, if T is a linear transformation from Rn to Rm, and it's defined by a matrix multiplication, then the column space of the matrix A is equal to literally equal to the range of T. And that is awesome. Now finding the basis of the range of T is the same thing as finding the basis of the column space of A, which is something we learned how to do already, but let's just take a look. So we're over here. Examples, what did it just say? 4, 5, 7, you saw two procedures to find the basis of a column space. The next two examples use the procedures from example 5 in section 4.6 to find the basis of okay. So we learned two different, right, back in 4.6, we learned two different ways how to find the basis of a column space. We're gonna look at an example now. We're gonna use one of those ways. Okay, so we want to find a basis for the range of a linear transformation, and it's a linear transformation from R5 to R4, the same one we had in example 6 of this section, to find and we want to use that to find a basis for the range of T based on this matrix. This is the matrix A that we used back in example 6. And first thing we did, if you remember, we reduced row echelon it to row reduced it, as they say, to this guy right here. So the leading ones appear in columns 1, 2, and 4 of the reduced matrix on the right. The corresponding column vectors of A form a basis of the column space of A. So a basis for the range of T would be column 1, column 2, and column 4 of the original matrix. Now, in other words, we're not taking this, that, and that. We're taking this guy, and that guy. Column 1, column 2, and column 4. That's going to be our. That's going to be the range of our that's going to be the range of our that's going to be, I'm sorry, the basis of our column space. Hence, it's the basis of the range of the transformation T. And that is just awesome. That is just awesome. Now, we're now going to give next definition here. The definition of rank and nullity of a linear transformation. Let T from V to W be a linear transformation. The dimension of the kernel of T is called the nullity of T and is denoted nullity of T. The dimension of the range of T is called the rank of T and is denoted by rank T. And notice here that the rank of T plus the nullity of T in the examples we just had before, which is 3 plus 2 equals 5, is the dimensions of the domain. So this relationship is true for any linear transformation, and this again is very, very similar to the concept that we saw in section 4.6 when we just talking about matrices. That's what the remark here says. If T is given by matrix A, then the rank of T is equal to the rank of the matrix A. The nullity of T is equal to the nullity of A. This whole definition really comes from the same definitions that we did back in 4.6. Good old 4.6. It's been a long time. So again, the sum of the rank plus the nullity is equal to n, where n is n-dimensional vector space. And of course, that's also going to be the number of columns as well. So, whoops, well, the proof is kind of what we just said. I'm not going to go through the whole proof because we kind of went through it already. It's kind of what we said already. So let's just look at the next thing. We want to find the rank and the nullity of the linear transformation from R3 to R3, which is defined by this matrix. So basically what I'm going to do is find the rank and the nullity of the column space. And since A is in, of the matrix, let's just say A is in row echelon form already, has 2 non-zero rows, so it has a rank of 2. I'm sorry, it's dimension of the whatever. I said the wrong thing, but you know what you guys know. So the rank of T is 2, and the nullity, which is the dimension of the domain minus the rank, is equal to 3 minus 2 equals 1. So that is awesome. And one way to I like this paragraph here. One way to visualize the relationship between the rank and the nullity of a linear transformation provided by a matrix is to observe that the number of leading ones determines the rank, the number of free variables, which is columns without leading ones, determines the nullity. So therefore the sum total must be the total number of columns in the matrix, which is really, we said the same idea back in chapter 4. So let's find the rank and the nullity of a linear transformation. Here we go. Example 9. So T is a transformation from R5 to R7. We want to find the dimension of the kernel of T if the range is 2. Dimension of the range is 2. We want to find the rank of T when the nullity of T is 4. And we want to find the rank of T when the kernel of T is the 0 vector. So dimension of the kernel is equal to n minus the dimension of the range. 5 minus 2 equals 3. Pal, that's our answer. And again, the rank of T is equal to n minus the nullity. So it's 5 minus 4 is 1. And the nullity of T is 0. So the rank of T is equal to n minus the nullity, which is 5 minus 0, which is 5. See how simple that's how simple it is. Sometimes sometimes it's funny. Sometimes the problem can be super complicated. Sometimes it's super simple. Now it's not really super simple, but sometimes we did the work. We got, and now we're sort of benefiting the fruits of our labor. So now it seems super simple, but a lot of hard work and complex work went into making this super simple, if that makes any sense. Alrighty, this is again so much. I don't spend a lot of time in class going over these different applications, but they were kind of cool and awesome. I suggest you read them, look at them. Okay, that's it for this. That's it for this video. That's it for this video. We're not done with 6.2, but that's the end of this video, and we will continue next time.